All right, well, I am glad that you all are here. All right, well, I'm glad that you all are here. Turn off my phone here. I'm going to go ahead and give you a brief introduction in case you didn't get a chance to click on the information in the video description area. So in the video description area, there is a link to a Google document, and there are 30 multiple choice questions. And what I did was I picked 10 questions from units 1 through 3. So let me go ahead and show you that. So those are all the 9 units. And I'm going to break this review session up into 3 parts. So there are 10 MCQs, or multiple choice questions, from units 1 through 3. And then there's going to be 10 MCQs for units 4 through 6, and then 10 more for units 7 through 9. And then what will happen is, instead of me just immediately going over these questions, I'm going to give you a chance to work on them. So whether you are using scratch paper, your calculator, trying to do it on, some sort of online device to kind of simulate Blue Book, I'm basically going to give you some time to work on these questions and give you about 10 minutes. I'm going to turn on a countdown timer. And then at the end of that 10-minute period, I will start going over the answers. But in the meantime, there will be an opportunity for you to go ahead and check your answers, because in that Google document, there is a link. There's also the QR code on this slide, and that allows you to either click on the link in the Google document or scan the QR code. You can actually start putting in A, B, C, D for these questions. And so you can find out if you got it right before you hear my official explanations. So I'm going to go ahead and turn on my timer. That way I can count down the first 10-minute period. So give me a second to do that. Okay. So again, what's going to happen is you're going to be working on these questions, and then you can double check by clicking on the link in the Google document or by scanning the QR code. You can say, do I think number 1, number 2, number 3, A, B, C, D. You can put in your answers, and it will tell you whether you got those honest than the actual AP chemistry exam timing. Why is it a little faster? Well, I'm only giving you about a minute per question. And the fact that you're only getting about a minute per question, that might not be enough time. So in the actual AP exam, it's going to be 90 minutes to answer 60 questions. So on average, you have about a minute and a half per question. But what you'll find is that some questions will take maybe 10, 15 seconds to answer. So that's why it's an average. But what you're working on right now are questions that are related to things in units 1 through 3. And then again, once that timer expires, I will go ahead and explain the process of answering these questions. If these questions, if they seem familiar to you, it's because I took them from my multiple choice question practice packets that are available on my channel. So I don't know if you had a chance to do all of these MCQs, but if you have a little deja vu while you're working on these questions, you might have seen them before. So yeah, this particular QR code on this slide is not to the packet. The link to the packet is in the video description area below this video. The QR code is simply going to give you a chance to put in A, B, C, D for all 10 of these questions, but the QR code in the Google form does not show you the actual question, so that link is in the video description area. Yeah, there's a Google document. I also posted a link to the like a PDF version of it, just to give you some flexibility, but the Google document should have everything you need. Yeah, I don't know. Hopefully I'm not glitching. I'm not sure if my internet is making this seem pretty smooth or not. So at a minimum, it's going to take you 10 minutes. Obviously, you get more time, about an average of 1.5 minutes per question on the AP chemistry exam on the multiple choice question. Remember, it's 90 minutes to do 60 questions. And then tonight we're not doing any FRQs, but I am happy to host an FRQ review session if you think that would be a helpful thing. So again, what I will do in my explanations is try to guide you through the content and give you some good test-taking strategies as far as how you can do the math or understand the concepts to eliminate the wrong answer and select the best answer. And yes, after this session ends, the recording will be available. So again, you still are working on these 10 questions. You are welcome to click on the link in the Google document or scan the QR code and put in your answers. It only lets you do it once in terms of this Google form. So if you rush through that process, it won't let you retake it a second time in terms of submitting your answers. But it just gives you a little preview of what the correct answers are before you hear me explain everything. So again, tonight we're going to do 3 sets of 10. So yeah, if you think it might be helpful to have me run a review session that is focused on FRQs from past pre-response questions, then I'm happy to do that as well. Okay, so answers will be revealed and explanations will be given in about 4 minutes. All right, I'm seeing that in the chat. Yeah, FRQs sounds like someone or several of you might appreciate some review sessions that I can set up for. I mean, it's very similar, I suppose, to what you might be seeing on the AP Daily videos, but I can run through, and there's one of the links in the Google document that I'm sharing with you tonight, that entire playlist with teachers such as Kristen Cacciatore and Alice Pudi and Dina Leggett and the other AP Daily presenters. There's a whole playlist of MCQ practice and FRQ practice that's on that playlist on the College Board's YouTube channel. But yes, I'm happy to set up some FRQ review sessions, whether that's tomorrow night or Monday night, really last minute. But I'm happy to do that. Again, I hope you find this wait period helpful. I didn't want to just immediately go over a question that didn't really give you time to process it. So some of you might not get through all 10. Others of you might just be sitting around waiting for the answers, but hopefully you are engaging at some level with taking a look at these questions on your own, or if you're in a study group, before you hear my official explanations. But all of these questions did come from my MCQ practice packets, some of which I did not change. Like these were actual AP questions that I just borrowed from a previous test. But others, many of these questions I just wrote myself to be similar in style to the format of the AP exam. So some of these are original and some of these are modified slightly, and some of these were the exact same question. But I'm hoping to give you a lot of deja vu on test day. You can say you've seen a lot of this stuff before. Yeah, so I'm going to show not only the correct answer, but like the explanation that leads to why that answer is correct, as well as why the other answers may be incorrect. So I will definitely go through the thought process of how to think about answering these questions. That will definitely reveal my kind of test-taking strategy. So again, this is possibly a repeat if you've already watched all of my MCQ practice videos, because you might have said, I think I saw this question before, but I just picked and chose, again, 10 questions from each of the 3 sets of units. So we're going to get, obviously, these 10, and then we're going to get 10 more for units 4 through 6, and then we're going to get 10 more questions for units 7 through 9. So a little bit of everything tonight. All right, well, we are winding down. I'm going to go ahead and switch over to my other screen so I can start revealing answers here. Now, what I will probably do, just because my camera might be blocking some of the question, or it might be blocking some of the graphics, I'm going to go ahead and switch my view so that the talking head in the upper right corner of the screen doesn't have to be there the whole time. So, all right. So let's go ahead and take a look at these 10 questions that you were working on. All right, so question 1, a student performed a gravimetric analysis experiment to determine the percentage of silver by mass in an alloy containing a mixture of silver and copper. A sample of the alloy is dissolved completely into a solution of nitric acid, and we are looking for the percentage of silver by mass in the alloy. So I'm going to give you sometimes a little diagram to indicate what actually happened. So this piece of metal, which contains a mixture of silver and copper, is dropped into nitric acid. So now we have silver ions and we have copper ions. And the purpose of this is to connect grams to moles. So there is a precipitate formed of silver chloride. So that solid that's sitting on the bottom of that beaker on the right is silver chloride. And it has a mass of 0.72 grams from the information in the table. So if we could turn grams into moles, then we could eventually turn moles of silver chloride into moles of silver, and then eventually grams of silver. If we could figure out how many grams of silver there are, which is going to be a number less than 2, then that would be the percentage by mass. The grams of silver divided by 2 grams, which is the mass of the alloy, and then times 100. So this is definitely about moles. So they filtered that precipitate, and they got 0.72 grams, but that's not 0.72 grams of silver, that's 0.72 grams of silver chloride. So I'm using the periodic table, And I'm actually skipping the convert to moles part. I'm just going to go straight from from grams of silver chloride to grams of silver. I kind of skipped the times 1 mole and then divided by 1 mole. So this is effectively the ratio, the mass ratio of how much silver there is in silver chloride. But this answer is not our final answer. That answer is just how many grams of silver we have divided by 2. So 0.54 is not a 54%. That might be a tempting answer for some people that got this far and they thought, oh, 0.54 on my calculator, is that the answer? No, the answer is not C. The answer is 0.54 divided by 2 and then times 100. So correct answer to question 1 was 27%. All right, on to question 2. This is about periodic trends. So I'm going to just talk about periodic trends and eliminate some wrong answers here because we have 4 sentences and some of them talk about ionization energy, some of them talk about atomic radius. There's a little bit of electronegativity in there, so we have to eliminate 3 of these choices. So ionization energy. What you're seeing here is a general trend about atomic radius. Ionization energy is going to increase from left to right across a period as the electrons are closer to the nucleus and more difficult to remove. Ionization energy will increase from left to right, but it decreases from top to bottom, and that's because now it's easier to remove those electrons. So based on that trend, there's carbon and silicon. The ionization energy of silicon is less than that of carbon. So we can eliminate choice A. There's sulfur, there's chlorine. So the ionization energy of chlorine is greater than that of sulfur. Well, I'm not saying that B is the correct answer, but so far that statement is true. I'm going to keep going. Now with atomic radius, well, there's chlorine and bromine. Atomic radius of bromine is larger than that of chlorine, so that's true. And then the last one says that something about comparing magnesium and calcium, but calcium is larger than magnesium. So I just eliminated 2 of the 4 choices, but now let's look at the justification or the explanation. This is from a video that I talked about electronegativity values, and you can see that they generally increase from left to right, they generally decrease from top to bottom. So there's sulfur and chlorine. Sulfur has a lower electronegativity than chlorine, but in choice B it says that sulfur has a higher electronegativity than chlorine. So we've now determined that the correct answer is C, and this atomic radius is related to the electron energy levels. So bromine has a greater number of occupied energy levels. So it has energy levels of 4, whereas chlorine stops at energy level 3. So greater number of occupied energy levels, larger atomic radius. C is the correct answer. All right, next question. This is a diagram in which on the y-axis we have potential energy, which gives us a measure of comparing the strength of the bond. So a phrase I normally use in my class is, the deeper the valley, the stronger the bond. The more shallow the valley in this curve, the easier it is to break that bond, or the weaker the bond. And then left to right, we're looking at internuclear distance. So further to the right, longer bond, further to the left, shorter bond. And we're comparing a carbon-fluorine bond, so CF, with a carbon-chlorine bond, CCl. And we're not looking at single and double and triple. We're just looking at 2 single bonds, but they're going to be related to the size of the atom. Now, this is not the correct answer, but just simply a slide in which it gives you a general idea of what this represents. So the valley is where the atoms are just right. They're not too close together and too much repulsion between the nuclei, and they're not too far apart. So their energy is most stable right there in that valley. And this is, again, hydrogen would have a bond length of 74, has a bond energy of around 436. The deeper the valley, the stronger the bond, a higher bond energy. So what I'm looking for would be fluorine and chlorine. Now, since chlorine is a larger atom, then that distance will be farther away. The distance between C and F would be smaller, but the distance between C and Cl would be greater because the atom is a larger atom, so there's going to be more distance between them. So If Cl is larger than F, then the CCl bond is longer than the CF bond. So when I look at that choice C diagram, it indicates that the CCl bond is shorter. So I can eliminate that one. And then the same reason for choice D. Well, now I've narrowed it down to either A or B, but what does a longer bond and a shorter bond have to do in terms of the bond energy? Well, a CCl bond is going to be easier to break because those atoms are farther apart. So I'm expecting a more shallow valley. So the deeper the valley, the stronger the bond. So the CF bond would be shorter and stronger. The CCl bond would be longer and, again, easier to break. So based on that, I can eliminate choice B. Correct answer is choice A. The CCl bond is further to the right, so it's longer, and it takes less energy to break, so that valley is more shallow. All right, well, rain's really coming down where I am, and I'm hoping that that's not affecting the signal or the sound, but I'm hearing it pretty close to where I am here in Charlottesville. All right, moving on to number 4. This is related to bond energy and bond strength, but this is not a covalent bond like we saw in question 3. This is an ionic bond. So this is definitely a Coulomb's law question. And what we're looking for would be smaller ions closer together, stronger Coulombic attraction, larger ions farther apart, weaker Coulombic attraction. So we're comparing the distance as well as possibly the magnitude of the charges. So we'll take a look at what we're comparing here in this question. But smaller would have stronger attraction and higher lattice energy because they get closer together. That's the denominator of Coulomb's law. But if I was comparing charges like +2 or +3, which I don't see in this question, I would focus more on the magnitude. So I'm really focusing on the denominator of Coulomb's law, which is the distance, because they're both +1 and -1 here. So smaller. Chlorine is definitely smaller than bromine, so therefore they would be closer together. But I'm looking for NABR. Since bromine is going to be farther apart from sodium because it's a bigger ion, I'm looking for an explanation for why it would be less than, but it's because the atomic radius of bromide is larger than that of chloride. So I eliminated choices A and C because they said that bromine was smaller than chlorine. But yeah, weaker attraction, larger distance between the ions, weaker attraction. Correct answer for number 4 is choice B. And again, that's because they're farther apart based on the atomic radius trend or the ionic radius trend. All right, question 5. We're still talking about bonding, but this has to do with formal charge. It doesn't come right out and tell you that it has to do with formal charge, but it says, which of the following indicates the more favorable representation of the bonding and provides the correct justification? So I'm going to go ahead and assign formal charges to each of the atoms in each of these Lewis diagrams. And if you don't remember how to assign formal charge, it's valence electrons minus the number of dots and bonds. Like that's how I do it. Valence electrons minus the number of dots and bonds. So for oxygen on the left, it's going to be 6 minus 7. For carbon in the middle, it's going to be 4 minus 4. And for nitrogen on that particular side there on the right, it's going to be 5 minus 5. And if you're wondering, shouldn't all the formal charges be 0? This is a polyatomic ion. So the sum of the formal charges is going to equal the overall charge on the polyatomic ion. So you're not going to be able to get 0, 0, and 0 since we have to have a -1 somewhere. So really it comes down to, is the -1 more preferred on the nitrogen or on the oxygen? And the general trend is if you can't get all of them to be 0, you want to put the negative charge on the atom that has a higher electronegativity. Oxygen is further to the right. Oxygen is more electronegative than nitrogen. So the preferred structure would put the negative charge on the oxygen, and that would be diagram number 1. All right, halfway done with this set. This is question 6. So now we're looking at intermolecular forces. We've kind of moved from Unit 1 to Unit 2, and now we're at Unit 3. The structural formulas and boiling points for 2 different substances are shown above. Each substance exists in the form of a liquid at 20 degrees Celsius. We are not predicting which one has a higher boiling point because that's already given to us, but we are looking at vapor pressure. So if you're not sure how vapor pressure relates to boiling point, It is an inverse relationship. So I'll show you a picture. The flask on the right has a higher vapor pressure and a lower boiling point, so it evaporates more easily. The flask on the left has a lower vapor pressure, but would have a higher boiling point. So again, there's an inverse relationship between those. So we have a higher boiling point for substance 2, which is polar, so it has London dispersion forces and dipole-dipole forces between its molecules. And then we have a nonpolar substance that experiences only London dispersion forces. Again, you didn't need to predict the boiling point that was given to you, but hopefully you know that the substance with the higher vapor pressure is going to be the one that has the lower boiling point. So our answer is substance 1. And it's going to be because it has weaker intermolecular attractive forces. So I'm going to eliminate choices C and D because we know it's substance 1, higher vapor pressure, lower boiling point, weaker intermolecular attractive forces. So this comment in part A, or choice A, about it having a larger and more polarizable electron cloud, that's not consistent with weaker attractive forces. So we're comparing the fact that there's a combination of LDFs and dipole-dipole forces for the substance 2, whereas substance 1 only experiences LDFs. Okay, so correct answer is B. All right, we're still going to be in Unit 3 here. And I like this question because it's not as hard as you think. I like this question because it's not as hard as you think. All right, so we're looking for, is the pressure of argon higher or lower? Or I should say, no, less than or equal. Those are my choices. Less than or equal to 12 atmospheres. So your first thought might be, well, the volume is bigger. So you might think of like, P times V equals P times V, but it's a different gas. There's a mass that is different. It's a different volume. So there's lots of things to consider here. So we have helium, which would be 20 divided by 4. We have argon, which is 400 divided by 40. So we have 5 moles of helium. That was pretty simple math. 20 divided by 4 is 5. And then we have 400 grams of argon, and divided by 40, that's 10 moles. So we have twice as many moles of gas in the flask on the right. But take a look at the volume. It's twice as many moles, but it's also twice as much volume. So we're doubling the number of moles in that flask on the right, but we're also doubling the volume. So we're not changing temperature. We're changing number of moles, and we're changing volume, but it's by the same proportion. So hopefully you can see that it's not less than, it's equal to. Now, choice C says something about if two gases are at the same temperature, they will have the same values for both pressure and average kinetic energy. That's not true. Just because you're at the same temperature, you will have the same average kinetic energy, but there's no reason why pressure would go along with that. So it's only temperature that would be directly proportional to kinetic energy. So it's the fact that we doubled both the moles and the volume. So compared to the helium sample, the argon gas sample has twice as many gas particles, but it also occupies a volume that's twice as much. So I don't think that question was as hard as you might have thought, but hopefully my explanation helped you. And if it didn't, obviously I will do my best after this session is over to pour more closely through all the comments and see if I can do a good job of clarifying any confusion that you might still have after this session is over. All right, let's take a look at questions 8, 9, and 10. This one is about a deviation from ideal behavior. And so it says that NH3, which is ammonia, shows a greater deviation from ideal gas behavior than methane, CH4, does. How can you tell there's a deviation from ideal gas behavior? Well, the observed gas pressure is not the same as the pressure that we would have predicted from the ideal gas law. But just because it deviates from ideal gas law behavior doesn't tell us the reason why. There's actually 2 different reasons in this particular topic. So it happens to be less. So deviation from ideal gas law, which is in Unit 3, it either could be because of the attractive forces between the particles, or it could be the fact that the size of the actual particles, the volume of the particles, is no longer considered negligible. So this is from my video on that particular topic, and so what I'm showing you here is that if there is an attraction between the particles, that would decrease the pressure slightly because now they're starting to feel an attraction to each other. So when they collide with the container walls, it's going to be with slightly less force, and so the pressure observed is less. If the observed pressure had been greater than that of the ideal gas law, I would have used a different argument about the size of the particles themselves no longer being negligible. So choice C is giving an explanation that's going in the wrong direction. If choice C were true about the whole volume of the NH3 molecules occupying a larger portion, that would cause the observed pressure to actually be greater. So it's about the attractive forces because in this case 2.78 is less than 2.84. So the observed pressure is less than that calculated from the ideal gas law. But had the pressure been higher than 2.84, I would have had to use an argument very similar to choice C. All right, this is a particle diagram that goes along with question 9. And what we have to do is look for the error in the student's drawing or the student's diagram. That's supposed to be a particle level view of the calcium chloride solution. So there's solid calcium chloride on the bottom, but there should be ions of calcium and ions of chloride in the solution. So calcium's a metal, chloride's a nonmetal, calcium's +2, chloride's -1. So they didn't give you the chemical formula of calcium chloride, but it should be a 1:2 ratio. And so I see 4 calciums and 4 chlorines. So that's the mistake that the student made. There should be 2 chloride ions for every 1 calcium ion. And there's no charge balance. So we have 4 times +2 is +8, but we only have 4 times -1 is -4. So the diagram should contain twice as many chloride particles as calcium particles. I think A might have been an attractive choice, but these aren't molecules of Cl2. These are individual monoatomic ions of chloride. All right, last one, and then we'll take a look at our next set. This is related to absorbance and Beer's law. So I'm going to go ahead and analyze this data. So that's increasing in terms of concentration. Absorbance would also increase, and if you do that math, you realize that that matches. That's the same proportion. So we're going to look for a mistake. That increases, if you do the math, but 1.4, so that matches. But at some point, one of these absorbance values will not seem to match the data, and it's right there. It's going to be something went wrong with sample number 5, because the absorbance is only 0.87, but if it was going to be following that same straight line proportion, that direct proportion between absorbance and concentration, we would have expected it to be around, let's say 0.9 something. So the fact that that doesn't match indicates that maybe that absorbance is less than what it should be. And so if the absorbance is less, that typically is because of a dilution. So it's right there. That's the sample that is less than what it should be. And so it's going to be related to things like water droplets. So smudges or dirt or fingerprints on the cuvette will actually block the light, but that would result in a higher absorbance. So that's a previous question from one of my other videos talking about if the cuvette had not been wiped clean, it would look something like that. But if you added water or there was somehow some extra droplets of water if you were rinsing it, then that would cause the absorbance to be too low. So it was sample 5 that had the error that didn't follow the pattern, and that was because of a dilution with water. All right, so you are now ready for your next set. Now you might have been working on these questions while I was giving you the explanation, so you might not need the whole time, but I'm still going to go ahead. I'm going to switch my view here to my Google Slides. So let me go ahead and change my view here to the next Google Slides. All right, so this is the wrong one. I have to advance the slide here. Let me just double check and see. I want to go with this one. All right, so yeah, timer's going. And Again, this particular set of questions, I'm still calling them like 1 through 10. They're not going to be called 11 through 20. This set would deal with things like chemical reactions, Unit 4, kinetics, Unit 5, thermochemistry, Unit 6. Yes, again, after this session tonight ends, this video will be available with all of that information, both the packet itself. If someone was unable to attend this session, they can get access to that packet, and they can obviously hear all of my explanations. So I will do my best to give you some time to work on these 10 questions, and then we'll repeat. I'll go through, explain why the correct answer is correct, why the other answers are incorrect, and kind of go through that logic of how do we know that the answer was, B or C or D. And then eventually we'll have our final set tonight will be for units 7, 8, and 9. Yes, you can definitely reach out both in the comments, and I think it's pretty easy to find a way to contact me via email. But yeah, I'll definitely check if this session, if you're finding that explanations didn't quite do it, or you have some clarification about things that didn't quite get explained in tonight's session, I'm happy to continue to look through comments to clarify things that are still concerning you. I'm happy to do that. Oh, I'm seeing this one comment about absorbance. Yeah, something that the light doesn't get through at all. I guess that would be an absorbance that's actually very high. I would say it's zero transmittance, but in general, the absorbance is a measure of kind of like what blocked the light. So the darker the solution is, the higher the absorbance. So if something were even like, pitch black, the absorbance would be very, very high. Okay, maybe some of the takeaways tonight are both positive and negative. You might say you're building your confidence with how well you can answer AP-style multiple choice questions. You might find at the end of tonight's session, where you need to focus, whether that's going to be, a particular unit or a particular style of question. Obviously, you have access to your calculator for the entire multiple choice question. So if I go through some calculations tonight and you think, how can I do that math in my head? You don't. You have the online calculator with Blue Book, the Desmos calculator, or your own personal calculator that you're using. But I did include in the Google document and all those links on the first page, like exam day tips, what to bring. There's a list of, the approved calculators. So there's all kinds of exam day, test day details that I included on that first page of the packet. But yes, you do have access to a calculator for the multiple choice section. So the questions, if you arrived late, they are in a packet that is linked in the video description area. So again, if you arrived late, besides just knowing that there are these questions available to you, we're doing 3 sets of 10. So the first set of 10 questions related to units 1 through 3, so things like moles and bonding and intermolecular forces and gases. And these sets of 10 questions will cover units 4 through 6, so things like chemical reactions and kinetics and thermochemistry. And in the packet, which again is linked in the video description area, there's also some helpful links about AP exam study tips and what to bring, and talking about Blue Book. There's also a link to the entire playlist of review practice videos that were prepared by College Board staff, so for previous years. So there's lots of MCQ and FRQ practice videos that are on that playlist on the College Board's YouTube channel. And again, the QR code that you're seeing is going to allow you to put in what you think the answer is before I reveal what the answer is to all 10 of these questions. So if you want to click on that Google form or scan the QR code, you're just going to be able to put in for these B, C, or D, and then you can find out immediately if you were correct. But I am going to explain the answers in about 3 minutes. And then we'll do that next set of 10 for units 7 through 9. And again, on the actual AP exam that's on Blue Book, you are able to jump around. You can skip questions, come back to them. You can answer questions in any order. So if you're deciding that a certain question on the Blue Book is not coming to you, you can skip it and come back to it and just mark it for review. But it's going to be 60 multiple choice questions in 90 minutes. And you do have access to a calculator. And then the FRQ section is actually 105 minutes. It's an hour and 45 minutes, and you'll have 7 FRQs. You'll see them on Blue Book, but you'll put your actual handwritten answers in the testing booklet that you will get on test day. So MCQs are going to be submitted electronically just by clicking A, B, C, or D, but then FRQs, you're going to put your actual answers into the answer booklet, and then that will get scored at the reading. So it sounds like from some of the comments I saw, maybe it would be good if I did another review session that focused more on problem-solving strategies for FRQ. So I can take some of the long or the short FRQs from recent years and kind of go through my strategy for how to come up with the answers to that. So that would be a good thing to work on. Whether I do that for tomorrow evening or Monday evening, I can definitely set up a review session where we have done so many MCQs tonight. Maybe it would be good to take a look at FR strategies. I can do that. Again, I'm glad that my videos are helpful. I know that you all are trying to not only get the best score that you can on the AP exam, but just to feel like all of this hard work has paid off. The fact that you'd like to make sure that the score does an accurate reflection of all of the hard work you've been doing this year. So I'm happy to help support you on that journey. We're getting close to the finish line here. All right, well, I'm going to switch my screen and we'll take a look at the answers to this set of questions involving units 4 through 6. Let me go ahead and switch. And again, as I mentioned before, I think just for the sake of not having my camera block any of the important information, I'm going to go ahead and just continue to show you the information, but I'm going to remove my, my talking head in the corner there. All right, let's go ahead and take a look at these questions. So this is a question in which you have to write the correct net ionic equation. Now watch out for an equation that might be balanced in terms of atoms, but is not balanced in terms of charge. So both atoms and charge are important to consider when you're writing the correct equation. And that's not only true for multiple choice, but if you write your own version of a net ionic equation and you forget to put a plus sign, or you put like a minus instead of a plus, or something like that, that can still make your answer incorrect. So it's not just atoms, it's also charge. Now we have a chemical experiment in which a piece of solid copper is added to a solution of silver nitrate. That means that at the beginning of this experiment, the reactant is solid copper. Looking at these four choices, I do see the S for solid, but I'm not really crazy about choice D because they're showing it as an ion instead of atoms. The silver should be in the form of aqueous ions. So that looks like I see the AQ symbol for all four choices, but one of them decided to write AgNO3 as an intact formula and didn't split it up into silver ions and nitrate ions. Again, this is a soluble substance. So I can already think that maybe choice B doesn't look so good because of AgNO3, and choice D doesn't look so good because they wrote copper ions instead of solid. So I have solid copper reacting with silver nitrate to produce solid silver, which is now sitting on the bottom of that beaker on the right, and then the copper ions. So you may remember those soluble snap ions. So the fact that I just balanced the equation by putting a 2 in front of the silver and a 2 in front of the silver nitrate, but I'm now going to split up the silver and the nitrate and the copper and the nitrate and get rid of my spectator ions. Okay, so there is my balanced net ionic equation. So solid copper reacting with silver ions. This is actually an example of a redox reaction in which copper is being oxidized and silver is being reduced. So copper is being oxidized from 0 to +2. Silver is being reduced from +1 to 0. But yeah, looking at the four choices, that equation is not balanced in terms of overall charge. There's a +1 on the left, and there's a +2 on the right. So it's balanced in terms of atoms, but it is not balanced in terms of charge. And then the nitrate ions are spectator ions, so that should have been split up. And then in choice D, they started off with copper ions instead of solid copper. As in, sorry, not the solid part, the fact that it's an atom and not an ion. So it should have just been Cu with no charge. All right, so that was number 1. Correct answer is C. This is a particulate representation of a chemical reaction, but what we have to do is actually go backwards, because what we're seeing is the product mixture, and we have to go back to the reactants. We're not coming up with a balanced chemical equation. They already gave that to us. But we have to imagine that if I'm looking at 1, 2, 3, 4 particles of QX2, which is a product, what happened is that there was an excess reactant left over at the end. So that's why there's 2 particles of X2 in that little reaction vessel. So that would be not something we can throw away. So the fact that I started with 4 particles of QX based on the ratio of 4 to 2 to 4, and I have 2 particles of X2 that were consumed, but there's additional 2 particles of X2 that are left over at the end. So 4QX and 4X2 is what I'm looking for, and that would correspond to choice B. So you're kind of going backwards from products to reactants on that one. All right, our next one is a challenging question. I would agree this is challenging because that last sentence definitely throws you. What's the approximate value for the molar mass of HX? So your first thought is, I don't even know what the chemical formula is. How am I supposed to figure out the molar mass? So a good clue is look at the 4 units that are all listed there in those choices. Grams per mole. So in your mind, you're thinking grams divided by moles. Now, they gave you the grams. They just came right out and told you it's 1.40 grams. If you could figure out how many moles of HX are present from the information in this question, then you can take 1.40 grams and divide it by whatever that number of moles of HX is, because that would be grams divided by moles. So this is an acid-base reaction. It's a 1-to-1 mole ratio between HX, that's a monoprotic acid, and then sodium hydroxide. And so we have volume and molarity for the sodium hydroxide, which means if you know volume and molarity, you can calculate the moles. And the fact that it's a 1-to-1 ratio, whatever the moles of sodium hydroxide is also the same as the number of moles of HX. So 1.40 grams divided by whatever that number of moles of HX is going to be. So this is volume times molarity to get moles. It's a 1-to-1 ratio. So 0.0115 is what I got when I did volume times molarity. Of course, it's volume in liters, which is why you can see I converted to liters. So volume times molarity is moles, as long as your volume is in liters. So 1.40 divided by that number that I just got for moles of HX. That's my molar mass. So units, grams divided by moles, kind of told you what you had to do there. Figure out the number of moles in the traditional way using volume times molarity. And then 1.4 divided by that number of moles, my answer is C. All right, next question. This is about what kind of reaction is this? Is it a precipitation reaction? Is it an acid-base reaction? Is it a redox reaction? Well, it does say a solid precipitate is formed. And when a solid precipitate is formed, the usual process is what you might have learned as a double replacement. So I've got some calcium chloride. I've got some sodium carbonate. It doesn't tell you what the precipitate is, but remember those soluble snap ions? Sodium's new partner is chloride. Calcium's new partner is carbonate. Sodium chloride will not be the precipitate because sodium is one of those soluble snap ions. So the solid precipitate is not sodium chloride. The solid precipitate is calcium carbonate. So there's our calcium chloride. There's our sodium carbonate. So calcium's new partner is carbonate. And sodium's new partner is chloride. But what's sitting on the bottom of the beaker or the test tube as a solid is going to be calcium carbonate. Sodium chloride contains a soluble snap ion, so that would be aqueous. So those question marks on the right change to S for calcium carbonate and AQ for sodium chloride. So there's your calcium chloride. Now you might say, but calcium and chlorine are not soluble snap ions. If they tell you on the AP chemistry exam that something is AQ, if there's an ionic substance and it says solution or aqueous, it doesn't have to contain a soluble snap ion. The soluble snap ions are not the only ions that are soluble. If they say that magnesium sulfate is soluble, then magnesium sulfate is soluble. So you're not memorizing every single thing that could be soluble. But if I have to choose between two chemicals on the right and I have to figure out which one's the precipitate, I can eliminate the one that contains the soluble snap ions as it's not the precipitate. So there's our precipitate, and now we're going to filter it. So what comes through the filter paper is the filtrate, and that would contain sodium, excess carbonate, and then this is our answer. The chloride is present in the precipitate. So during the course of the experiment, what happens to the chloride ions? They're not in the precipitate. They're still dissolved. They're going to be in the filtrate solution. They're not going to be oxidized, forming chlorine molecules. They're not going to be reduced. So this was a precipitation reaction, and sodium chloride is now remaining in solution as a soluble product. All right, question 5. Now we're on to kinetics. Okay, so those first 3 or 4 questions were about Unit 4. This is Unit 5. Doesn't quite tell you if it's first order or second order. All we see is that the concentration is decreasing over time. Now, you could take the natural log of all those numbers and decide if that was linear. That would take a long time. You could also just, create some kind of graph on your calculator and try to figure out which one's linear. But let's see if another feature of first order kinetics can be determined. So what's half of 5.76 might actually show up in this table. So half of 5.76 would be the time it takes to reduce that concentration by half. That's the half-life, and that would be constant when something is first order. So if the half-life is constant over time, then it's going to be first order. And 0.693 divided by k equals the half-life. But if we know the half-life, then 0.693 divided by the half-life equals the rate constant. And that's what we're going to do in this question. So half of 5.76 is 2.88. Half of 2.88 is 1.44. Half of 1.44 is 0.72. And so that is decreasing by half every 4 minutes. So if the half-life is 4 minutes, now we know how to figure out the value of the rate constant k. So back to the equation sheet, 0.693 divided by k equals the half-life. Let's just swap those variables around. 0.693 divided by the half-life equals k. And that works out to be 0.173, and the units are inverse minutes. So correct answer is A. All right, still talking about kinetics. And this question is one of those deceptive questions, because when you see a question like this, you're very tempted to say, is it first order, is it second order? But it turns out you don't need to do that, but I'll go ahead and just pretend that I don't really know exactly what's going on here. So I'm seeing this potentially as a, did they double from trial 1 to trial 2? Did it double the rate? Is it first order, second order? So this would be a similar type of question. You know, they doubled the concentration of this chemical, they doubled the rate, so it's first order. So you could do all of that. But sometimes what we do on the AP chemistry exam is we think we know what the question is asking, and then we don't read carefully. They're not asking for the rate law. What they're asking for is in trial 2. Just trial 2. They're not asking to compare trial 1 and 3 or 1 and 2 or 2 and 3. They just want to know which is consumed more rapidly in trial 2. So it turns out knowing the rate law doesn't help you at all, because rate laws are related to changing concentrations from one trial to another. Okay, so the order with respect to a particular reactant will tell us how the rate is affected when the initial concentration of a reactant is changed. We're not changing initial concentrations, we're simply looking at trial 2 and only trial 2. So this idea of because it's second order, it's more about stoichiometry. And so I'm showing you on this slide something from one of my other videos where if something is decreasing or increasing, reactants and products, the rate of change is going to be proportional to the coefficients or the stoichiometry. So if something is increasing twice as fast as the other one is decreasing, the change in concentration for the products is happening twice as fast as the change in concentration for the reactants. That's based on a 2-to-1 ratio. Now let's go back and look at this question. There is a 2-to-1 ratio. So which chemical is consumed more rapidly is because there are 2 moles of Y consumed for every 1 mole of X consumed. So it's about the stoichiometry. The rate of disappearance of Y is twice as much as the rate of disappearance of X. And that had nothing to do with the rate law. That was just stoichiometry. So sometimes we go down that road of we think we know what the question is asking, but order, first order, second order, that's about changing from one trial to another. And we didn't need to do that in this particular question. So correct answer is D. So yeah, stoichiometry was how it was going there. It wasn't about the order. So that's just a comment about that stoichiometry was showing us which reactant is consumed more rapidly. The order tells us how the rate is affected when the initial concentration is changed. All right, moving on to question 7. Still talking about kinetics, but not every collision between particles will be effective. They have to be lined up. They have to be oriented in a certain way. So which of the following orientations of the collisions between the particles is going to be effective. So how do you answer a question like this? Look at the bonds that are being formed. Look at the bonds that are being broken. So in choice A, it looks like an oxygen is colliding with an oxygen. In choice B, it looks like an oxygen is colliding with a carbon. In choices C and D, it looks like a nitrogen is colliding with something. So I don't think new bonds are being formed between nitrogen and anything. But considering that the collisions have to be properly oriented, I'm looking for, did the model get it right based on the bonds that are being formed or broken? So CO turns into CO2, which means that that carbon needs a new bond to another atom of oxygen. So I'm looking for a new bond to be formed between the carbon and the oxygen. That's why choice B is the correct answer. A new bond is formed between an atom of carbon in black and an atom of oxygen in white. So correct answer is choice B. All right, question 8. Now we're looking at unit 6. So this is about thermochemistry. And if the temperature gets hotter, you have to consider, is there a Bunsen burner or a hot plate involved? If the temperature gets colder, what you're considering is there a Bunsen burner or a hot plate involved? And this is not about a Bunsen burner or a hot plate. You're simply dissolving something in water. So if it gets hotter, that is exothermic. It's just releasing heat to the surroundings, and that would be the water molecules in the solution. It's getting colder. It's going from 21 to 18, so this is an endothermic process. Which of the following best helps to explain the energy change that occurred? This is an endothermic process because it got colder. So in my other videos, I talk about system and surroundings. Generally, thermometer is considered part of the surroundings and not the system. If it gets hotter, exothermic. If it gets colder, endothermic. And again, I'm not talking about a hot plate or a Bunsen burner, just simply you mix chemicals together. If they get hot all by themselves, that's releasing heat. If they get cold all by themselves, that must be absorbing heat from the surrounding water molecules. So like a cold pack. It's endothermic because heat is flowing from the surroundings to the system, but it feels cold on the outside. Now that I know it's endothermic, I'm looking for bonds being broken or formed, or attractive forces being broken or formed. So I'm looking for something that relates to attractive forces that are being broken. So when Ki solid dissolves in water, ions of K plus and I minus are formed. When Ki solid potassium iodide dissolves in water, molecules are formed. Breaking attractive forces is an endothermic process, so I'm looking for something being broken. Forming attractive forces is exothermic. That's not what I'm looking for. So in this particle level view, step 1 and step 2 are endothermic process in which attractive forces between the solute or the solvent are being broken. Step 3 is exothermic. I'm not looking for that. So the correct answer is something in which attractive forces are broken, since we already know this is an endothermic process. So K plus ions have very strong ion-ion attractions with the I minus ions in the crystal lattice. Those would be broken when that solid dissolves in water. Choice D, K plus ions have very strong ion dipole attracted interactions with water molecules, but that would be formed, not broken. So correct answer is choice C. So you're connecting the endothermic nature of the overall process with something at the particle level involving breaking attractive forces. All right, question 9 is a phase change question. And I really like this question, so I'll try to explain it clearly, but at first glance you might think, what the heck is going on? Because we're mixing gallium with gallium. Sample of gallium at room temperature-ish, a little bit warmer than that, I guess, it's 29.8 degrees, is added to 100 grams of liquid gallium that's pretty hot. Liquid gallium is 83.9 degrees. So the hot stuff's going to get cooler, and in the process, the mixture is stirred gently until the temperature reaches 29.8 degrees. So what's so special about 29.8 degrees? Well, in the table, that is the melting point. So what happened is some solid melted. And based on the information in the table, we got to figure out how much gallium had melted. So why did the gallium melt? Well, because a hot liquid was added to it. So hot liquid gallium was added to a lower temperature of solid gallium, and all of it melted. Well, I wouldn't say all of it, but a certain amount of it melted because it says at the end they took any remaining solid gallium out of the container. So I'll give you a picture here. So there's our liquid gallium, which is the hotter temperature. Here comes our solid gallium. We just don't know how much that solid weighs. It goes in and it melts. Final temperature is 29.8 degrees. So the heat that was lost by the liquid gallium is equal to the heat that was gained by the sample that melted. So if we could do MC delta T, we could figure out how much heat was lost by the liquid gallium. And how do we know it's MC delta T? Because we have an M, which is the mass of the liquid gallium. We have a C, which is given to us in the problem, so specific heat capacity of liquid gallium. What's our delta T? It was 83.9, and now it is 29.8. This is the heat that was lost by the liquid gallium. But that's also the heat that is gained by the solid. So we're only one step away from figuring out the answer. 80, said, looking for the decimal there. 80, with the little decimal there, joules per gram means that it takes 80 joules to melt 1 gram of gallium. It takes 80 joules to melt 1 gram of gallium. Well, we have 2001.7 joules. Let's go divide that by 80.1, and then that will be our answer. So 25 grams of solid gallium melted. If that question seemed challenging to you, I would just simply focus on the diagram that I showed you earlier. Okay, so we have a hot liquid. Here comes the solid, and it all turned into one thing. And that one thing was at 29.8 degrees. So the heat that was lost by the liquid as it cooled down is equal to the mass of 25 grams of gallium that melted because it absorbed exactly that amount of heat. So correct answer is choice C. All right, last one. This is stoichiometry, so limiting reactants as well as thermochemistry. So if I read this equation, 2 moles of C2H2 react with 5 moles of O2 to produce 4 moles of CO2 and 2 moles of H2O, and it's negative 2,600 kilojoules per mole of reaction. Now, what's the limiting reactant? Well, 3 moles of C2H2, according to the stoichiometry, would require 17.5 moles. I don't have 17.5 moles of oxygen. So that's the limiting reactant. Let's go the other way just to confirm that. 6 moles of O2 would require 2.4 moles of C2H2. Oh, I've got plenty. I've got 3 moles of C2H2, so that's definitely the excess reactant. So my limiting reactant will not only limit how much product is produced, the limiting reactant will also limit how much heat is produced. So I'm going to eliminate choice A and B. I know my limiting reactant is oxygen, and now I'm going to convert 6 moles of oxygen. I'm going to convert that into kilojoules. So the limiting reactant is 6 moles of O2. For every 1 mole of reaction, that would be 5 moles of O2. And for every 1 mole of reaction, that would be 2,600 kilojoules. So correct answer is 6 divided by 5 times 2,600. So 6 divided by 5 times 2,600 is choice D. So it's approximate. So the limiting reactant limits how much heat was released in this experiment. All right, your next set is coming up. Let me go ahead and switch my screen here. All right, I'm going to advance my Google slide. at the end of this set of questions. Hopefully you will feel like you've seen a little bit of everything tonight. So again, these particular questions will be equilibrium, Unit 7, acids and bases, Unit 8, thermodynamics and electrochemistry, Unit 9. Again, hopefully in some of the questions you feel like it matches where you are in terms of your understanding of the content and your strategy for answering questions, but hopefully even if you got the question wrong, you have a pretty good idea of whatever mistake you made, or maybe it might strengthen your understanding of the content so you can face additional questions with more confidence. So that set of MCQs we're looking at tonight, all of these did come from my MCQ practice sets. I just sort of pulled a few from each unit. So if you do want more practice with MCQs, in addition to all of the great resources that are available on AP Classroom, there's practice tests available through AP Classroom, but if you need MCQ focus, there's lots of videos for all of the 9 topics on my YouTube playlist for AP Chemistry CED units, organized by the 9 units. So again, our final set of 10 will cover equilibrium, acids and bases, and a mixture of thermodynamics and electrochemistry. And I will definitely let everyone know, again, whether that's tomorrow evening or I know Monday evening is kind of last minute, but at the same time, it is what it is. I will let you know. It sounds like FRQ strategies would be a good session to hold. So I will either do that for tomorrow evening or Monday evening, I'm not sure, but I will let everyone know, absolutely. So again, if you are using the Google form, it will tell you whether your answers that you're submitting on that Google form are correct or incorrect. It will tell you what the right answer is, but I will be doing the same that I have been doing for the next set of 10. I'll be going through my problem-solving strategy to try to explain why the correct answer is correct and why the other answers are incorrect. And like I mentioned earlier, on that first page of this handout or this packet for this session, there's lots of helpful links, and one of the links that I shared is to the YouTube playlist of test-taking strategies, MCQ, FRQs that were presented in previous years by the various College Board presenters, the AP Daily teachers. So if you're looking for additional videos that were from College Board presenters, that playlist is on the first page of this handout. So if you'd like to go back to last year or 2 years ago and watch any of those test-taking strategy videos, those would be another good resource. And with respect to Unit 8 specifically, I think that Unit 8 can be, for some students, kind of overwhelming. It depends on whether you did learn the 9 units in order. So it might be that you just recently, in the last few weeks or a month or so, did all of your acids and bases and buffers and titrations and things like that. So that can be fresh in your mind, but it can also be challenging with respect to applying your knowledge of equilibrium to acids and bases. So again, I'll do my best to explain these 10 questions, which include equilibrium, acids and bases, and thermodynamics and electrochemistry. But if you want more problem-solving strategies, again, you can take a look at some of the other videos on my channel that you can focus on if you need a refresher of something like buffers or electrochemistry or Le Chatelier's principle, Q versus K, things like that. All right, answers coming up in about 3 minutes. And again, after this session ends this evening, I will do my best to set up a session for free response question practice and strategies for answering free response questions. I will also take a look at comments with respect to anything that needed to be clarified, if something was unclear, because I might have gone a little bit too fast and didn't give you a chance to process. So feel free to ask follow-up questions and then be on the lookout for FRQ review session either tomorrow evening or Monday evening. And again, all of these MCQs that you're looking at in this review session, these were borrowed from my various MCQ practice packets. So again, you might have already seen them before, in which case you didn't see anything new this evening, but I just tried to put them all into a collective so you have a chance to think about reviewing a variety of topics. So if you need to watch any of my videos for MCQ practice or just in general for content, they are available. But yeah, I think the plan will be FRQ practice for my next review session, whether that is tomorrow, Sunday the 4th, or whether that is Monday the 5th as a night before the exam review session. So I can definitely work on that. All right, answers coming up in about less than a minute here. All right, I'm going to transition over to slideshow. All right, so these questions deal with equilibrium and eventually acids and bases and thermodynamics and electrochemistry. All right, this is a Rice table question. So again, a Rice table reaction, initial, change, equilibrium. So what do we know? Well, we know the Kp, and we know the partial pressure of xy at equilibrium. So again, this is reaction quotient, equilibrium constant. So there's lots of Unit 7 topics here, making a Rice table. So I'm going to fill in As much as I know, I don't know that number. A pure sample of XY is pumped into a previously evacuated rigid container. But there's nothing else in there, which means the initial pressures would be something I don't know, and 0 and 0. The partial pressure of XY is equal to 0.5 atmospheres at equilibrium. We'll go put that into the final row of the Rice table. Now the good news is we actually have the value of Kp. So since we have this 1-to-1 mole ratio between the products, even though I don't know what those pressures are, I know they are the same. So based on the 1-to-1 mole ratio of the chemical equation, the partial pressures of X2 and Y2 should be the same. So I have an unknown times itself. That's going to be like that number squared, so X squared on the top. On the bottom, I have 0.5 squared, and that's going to equal the Kp. So X times X divided by 0.5 squared equals 9. Now, 9 times 0.5 squared is 2.25. Square root that number. So those are my pressures at equilibrium. Well, I can now go backwards, considering that I have a ratio of 2 to 1 to 1. I need the change row of this Rice table to be in that same ratio of 2 to 1 to 1. So if each of these increased by 1.5, I need the change in xy to be proportional based on the coefficients. That means it decreased by 3. Now, the answer is not 3. It's how much was the initial pressure in the container. So that would be 3.5. So it was a Rice table. You had to kind of just work backwards from products to reactants on that. All right, so question 1 is D. This is a Q versus K kind of a question. Which of the following sets of initial conditions would lead to the formation of more XY3, which is a product? So if Q is less than K, we will proceed from left to right or from reactants to products. If Q is greater than K, we will proceed from right to left or from products to reactants. And so because we're looking for more XY3, I need Q to be less than K. So Q is going to be less than K. That means that 3 of the choices will have Q greater than K. And that would be going in the opposite direction. So now it just becomes pick up your calculator and plug in these numbers. So we are not at equilibrium, but let's go ahead and see if Q is less than K in one of these 4 choices. So in choice A, when I did that math, 2 squared divided by the product of 0.5 times 1.5 cubed, 2.4 is greater than 0.4, so I eliminate choice A. Now I'm doing 1.5 times 4, I'm doing 4 squared divided by 0.5 times 1.5 cubed, so that is even larger than what it was in choice A. So that is also going to be eliminated. So I've now narrowed it down to either C or D. And it turns out that when I did this math, I just found my answer. 0.15 is less than 0.4, so that makes C the correct answer, and then just to confirm that choice D, that value of Q is greater than 0.4, so C was the answer. That was a Q versus K, and again, Q is less than K, so we're moving from left to right or from reactants to products. All right, this is also equilibrium, but this is KSP. So we mix these 2 chemicals together, and if Q is greater than KSP, then there will be a precipitate. If Q is less than KSP, then there will not be a precipitate. So let's go ahead and figure out moles. And we're going to start with moles by doing volume times molarity. So let's go ahead and figure out the moles. If Q is greater than KSP, then a precipitate should form. If Q is less than KSP, a precipitate should not form. All right, I'm going to figure out the moles. So volume times molarity will give me moles of lead. Volume times molarity will give me moles of chlorine or chloride. And so now I can put them in the same container, which means that the total volume is 100. I'm going to take these number of moles and divide by the total volume. So when they're in that beaker on the right, total volume will now be 100. So I've got my molarities at the moment that those 2 solutions are combined. So that's moles of lead divided by total volume of 0.1 liter. I've got moles of chloride divided by total volume of 0.1 liter. And I'm going to plug these numbers into my Q expression. If Q is greater than KSP, then I will see a precipitate. So what I got was 8 times 10 to the negative 6, but that is less than 1.7 times 10 to the negative 5. So my answer is lead chloride will not precipitate because Q is less than KSP. Well, this question is more about acids and bases, but it does relate to Le Chatelier's principle. It relates to an equilibrium going on for a weak acid. So what we have here is 3 different solutions of the same weak acid. Now, the value of K can only be changed by temperature. That's not happening here. So choices A and B say the value of Ka would either going to decrease or increase, but we're not changing the temperature. So it's either something about the percent ionization decreasing or increasing. So what is percent ionization? Percent ionization is how much H plus or hydronium do we have, and that's listed in the table, divided by the initial concentration of the acid, which is also listed in the table. So we can do hydronium concentration divided by the initial weak acid concentration and then times 100. And it turns out that when you dilute a weak acid, something happens with respect to Le Chatelier's principle. You actually increase the percent ionization. So there will be a decrease in the overall concentration of all of the aqueous species. But when you decrease the overall concentration of all the aqueous species upon dilution, you have a Q is less than K situation. So it turns out that weak acids will become more ionized, a greater percent ionization upon dilution. So again, mathematically, we can see that the percent ionizations are increasing when you dilute a weak acid. Basically, the equilibrium is shifting toward the side of the equation that has a greater number of moles of aqueous particles. So that happens to be on the right side of the equation. So percent ionization of a weak acid will increase upon dilution. All right, still in the world of acids and bases, this is about which has the highest pH. Now, acids would have a pH less than 7. Bases would have a pH greater than 7. So highest pH would be, are they behaving like an acid or a base? If they're behaving like an acid, that would not be the highest pH. We're looking for a base. So HF and HCN are weak acids. I'm looking for either the CH3 parentheses 3N, which is the trimethylamine, or I'm looking for the aniline, which is the C6H5NH2. One of them is the stronger base. But we don't have the Kb values. We have the pKb, so watch out for that. Just because 9.42 is larger than 4.19, that doesn't mean you have a stronger base. So it's the 10 to the minus pKb would give us the value of Kb. So it turns out that the lower the pKb value is, the higher the Kb value is. And that makes the choice C substance with the higher Kb the stronger base. So that would have the highest pH because it's the strongest base. So number 5 is choice C. This one is a particle diagram that we're supposed to figure out where that would be along this titration curve. So I'll just show you my particle diagrams from another video for topic 8.5. So we start out with a weak acid, and eventually we have turned all of that HA, or that weak acid, into A minus. At the halfway point, we have an equal amount of the weak acid and its conjugate base. If we're before the halfway point, there's more HA than A minus. And if we're after the halfway point, then there's more A minus than HA. So let's count the particles and see where we are in this titration curve. I see 2 particles of HX. I see 4 particles of X minus. So we are past the halfway point in the titration. So that makes choice C the correct answer. Had there been an equal amount of HX and X minus, it would have been choice B. And had there been more HX than X minus, it would have been choice A. If we had a majority of particles as X minus, it would have been choice D. All right, still in the world of acids and bases, this is about a buffer. And you can make a buffer by combining a weak acid and its conjugate base. You can make a buffer by combining a weak base and its conjugate acid, but there's another way to make a buffer. You can do a titration as long as you stop halfway. Just like I talked about in this question, the halfway point in a titration would be equal amount of the weak acid and the conjugate base, or the weak base and the conjugate acid. So we're going to do a half titration in question 7 to make a good buffer. So we have half titration. At the half titration point, the concentration of the weak acid is equal to its conjugate base. So that's going to make a pretty good buffer, whether that's HClO2 and ClO2 minus or HF and F minus. You can make a buffer with an equal concentration of a weak acid and its conjugate base. So one way to make a good buffer is to do what I would call a half titration. So the half equivalence point would get you to that good equimolar mixture that you need for a buffer. Now, in all 4 of these choices, we have a weak acid. In all 4 of these choices, we have a strong base, but we don't want to go all the way to the equivalence point. We want to go to the halfway point. So choices C and D are going to go all the way. Choices A and B are going to go halfway. So the correct answer is either A or B. So choices C and D would result in the equivalence point where all of the acid was turned into its conjugate base. So it's either going to be choice A or B. That would be a good buffer solution. And now, which would be a good buffer solution at a pH of 3? Let's take the negative log of the Ka and see which one looks pretty close to around 3. So the pKa is approximately 3 for the HC3H5O3. And if we could neutralize or react with strong base, not all the way, but just halfway, that would be a good buffer solution. So correct answer to question 7, going to the halfway point in the titration would be a good buffer. That would be choice A. All right, questions 8, 9, and 10 are going to be falling under Unit 9, which is thermodynamics and electrochemistry. So this one's about delta G, delta H, T delta S. I'm going to go ahead and plug in my numbers, but watch out for your units because delta S is in joules and delta H is in kilojoules. So watch out for your units. I've got negative 426 for delta H, and I've got negative 18 for delta S, but those units don't match. So before I plug in that number for delta S, I am going to divide by 1,000. Now when I do that math at 298 Kelvin, if I get a negative delta G, then my answer is either A or B. If I get a positive delta G, then my answer is either C or D. And when I did that math, I happened to get a negative delta G. So my answer is either A or B, and it says, what about T delta S? Is it smaller or larger in magnitude? Now magnitude would be an absolute value. So negative 5.4 is the value of T delta S, but the absolute value would be 5.4. So that is a smaller magnitude than 426, so that makes choice A the correct answer. So just watch out for your units when you're plugging in delta S and delta H into that equation. All right, I think some electrochemistry is coming up, so there's a galvanic cell. And we have to figure out whether the potassium ions are moving toward the cathode or toward the anode. Well, potassium ions are positive ions, and cations always go toward the cathode. Reduction occurs at the cathode. So that means that the cations will need to go to the site where reduction occurs. So cations move toward the cathode in order to balance out the loss of positive charge in the cathode half cell. So reduction at the cathode, oxidation at the anode. Since the salt bridge contains potassium and nitrate, but potassium is a cation, it's going to flow toward the cathode where reduction occurs. So the correct answer is either B or D, but now we don't know what's being reduced until we add these two half reactions together. So we know that potassium's flowing toward the cathode, we just don't know which one is the cathode. I'm going to go ahead and flip one of these equations, and the one I'm going to flip is such a way that I can add them together and have them be positive. So if I were to flip negative 0.13, well, that would become positive 0.13, but then that would equal a negative overall if I added it to the other equation. But if I flip negative 2.37, it becomes positive 2.37. And I did that on purpose so I could get a positive cell potential for this galvanic cell. So now, who's being reduced? Well, lead is going from +2 to 0. Magnesium is going from 0 to +2. So lead is being reduced. Magnesium is being oxidized. So the potassium ions are going to be flowing toward the reduction half reaction, and that would be the lead that's being reduced. So correct answer is B. All right, last one I think is also about electrochemistry. Let's take a look. It's a calculation of delta G, but we're not using delta H minus T delta S like we did earlier. We're using delta G equals negative N, which is the number of moles of electrons. And that will turn out to be not 2, not 3, but 6. Now, a very important point, if you multiply each of the coefficients by 2 or by 3 to get the electrons to cancel, you do not, repeat, you do not multiply the voltage. So the only thing I did to manipulate those half reactions is I changed the sign of the aluminum half reaction. I changed it from negative 1.66 to positive 1.66. I did not multiply the voltage or the cell potential by 2 or by 3, so be careful you don't do that. Leave the cell potential the same except for just changing the sign when you reverse it. So my answer for the voltage is positive 1.66 plus negative 0.76. There's my electrons canceling out. And my number of electrons is not 2, not 3, but actually 6. My number of electrons is 6. So there's my equation with the 6 times the Faraday constant times the 0.90 voltage for the cell potential. And so it's approximately negative 520,000, but that would be a coulomb times a volt, which is a joule. So it's about negative 520,000 joules or negative 520 kilojoules. So correct answer is A. Now, I will go ahead and switch over my view to just regular. I will tell you that if the multiple choice questions that you were working on this evening, if they were a struggle, again, you can let me know in the comments, but you can also find some of those MCQ practice packets and videos on my YouTube channel. But it sounds like whether it's tomorrow evening, Sunday evening, or whether it's Monday evening, I will definitely set up another live session, but this time I will focus my attention on free response questions in terms of problem solving. So hopefully you found all of these answers and explanations helpful. I think I try to avoid the phrase. I haven't said it in all evening. I didn't even say it once. These are the answers. Yeah, I didn't do that at all. Anyway, but I do appreciate you all working this evening on these questions. I hope it was helpful. Thanks for watching, and stay tuned for the next live session on free response practice. All right.